Hi, everyone. My name is Ziquei Liu from the Department of Material Science Engineering, Pennsylvania State University. I would like to thank the organizers for asking me to give a presentation at this conference. The title of my presentation is Zentropy Theory for Properties of Rare Earth Elements and Compounds, using serine and yttrium as example. In 1966, Gibbs and Harvey published their book titled Properties of the Rare Earth Metals and Compounds. The properties included in the book are the physical, chemical, magnetic, electric, mechanical, and nuclear properties of elements and their compounds, rare earth elements and their compounds. In this book, there are many tables, including a wide range of properties. I highlighted a few of them here, such as the volume, some expansion, Curie temperature, and Young's modulus. As you may know, many of them are related to free energy and its derivatives. So let's look at the derivatives of free energy. We first look at the combined law of thermodynamics in terms of internal energy. The du is function of entropy, volume, moles of components, and internal degree of freedom can be written as this differential equation with y dx minus d psi. X are the potentials here, such as temperature, stress, pressure, electrical, magnetic fields, and chemical potentials. X here are the molar quantities, such as entropy, strain, volume, electric, magnetic, displacements, and moles. And psi is internal degree of freedom for non-equilibrium systems. So the free energy is defined by remove one pair or more pairs to the left side. So the internal minus the potential times the molar quantity. Then this to switch position. Now we have x dy instead of y dx here. And the other one's not switched, which will be y dx and minus d psi. The first derivative would be like if the u internal energy to x derivative give y, like temperature and volume. And however, if we take the Gibbs energy function to derivative to p, will give the volume. Okay, so it's potential and the molar quantities. And the second derivatives are more complex because now we have two variables, could be two molar quantities, such as volume and entropy. So we get some expansion. And the relation between these two are the Maxwell relation. And now if we could have one potential and one molar quantity, then we get a new set of properties, which are not often discussed in the literature. For example, if the chemical potential of a component to a temperature derivative, that would be partial molar entropy, would give the solidity coefficient. If the electron chemical potential derivative to temperature, then the electron, the partial entropy of electron, which give us Seebeck coefficient. We also have set derivatives. For example, the linear electro-optical Poker effect, which is free energy, set derivative of free energy to electric field. So now it's clear that this coefficient is actually, sorry, this table lists all the second derivatives of free energy, which is first derivative between the potential and molar quantity. We get all the heat capacity, elastic properties, permittivities, permeability, and the thermodynamic factor. And this variables are positive. Then we also get is between the non-conjugate variables, y and x are not pairs. For example, say expansion is volume to temperature, as we just discussed. Appears electric is the electric displacement to the stress derivatives. So all these are the physical properties which we measure, except the blue ones. Those are between two potentials. Okay, so it's this way to thermal transport, stress transport, electrical migration, magnetic migration, and they are discussed in these three papers wrote in the last several years. And the diagonal terms are positive, but off diagonals could be either positive or negative. And the blue ones are the new set of quantities, and which are very useful for the cross phenomenon. For example, I want to mention some expansion could be either positive or negative. So we'll show some examples in this talk. Now, if this is between the two potentials, and there could be some more between the two potentials, such as the electric field to stress field. Okay, so that would be the electromechanical properties. So these are the blue ones are the very important new set of derivatives, which are very important for the properties of functional materials. So when we talk about free energy, there are usually two of them which we use often. They are Helmholtz energy and Gibbs energy. So how do we get them? So we do experiments. We measure heat capacity, we measure chemical activities, we measure electromotive force of phase transitions. Then we can evaluate the Gibbs energy or Helmholtz energy. For instance, most of Gibbs energy from this experiment data. We can also get it from computation. So what we can do today is the quantum mechanics based on density functional theory, which is predictive because it doesn't require the experimental input. So we have the data from the experimental computation, we do cathode modeling. Okay. We model the Gibbs energy as a function of a temperature, pressure, and composition. And then we develop the databases and the tools, and they can do material design, which are widely used in academia and the industry. However, there are some limitations of this method because it needs experimental data. The experiments we know are expensive and time-consuming, and it's not available for new materials. So the question is that can Helmholtz energy or Gibbs energy be accurately predicted, particularly magnetic properties for rare earth elements and their compounds? So let's have a look at what happened, what was the history of thermodynamics. So 150 years ago, and Gibbs developed the classical thermodynamics. We call it equilibrium thermodynamics in the 1970s. That's after the first industrial revolution, when the first law and second law were developed, and the Gibbs combined them together, developed a combined rule for equilibrium system. And about 30 years later, he developed statistical mechanics. And in the 1920s, quantum mechanics was invented. Then followed by the quantum statistical mechanics, and in the 1960s, the density functional theory. And the non-equilibrium system, as you can see here, we have equilibrium thermodynamics, but most of the systems have a non-equilibrium. So the non-equilibrium system was developed as kind of as another branch, different from the equilibrium thermodynamics, by Ansag and Brigot in the 1930s and the 50s. I want to emphasize in the 1970s, the cathode method was developed. Modern individual phases is digitization of the thermodynamics and applied for the cathode-based material design in the last 50 years. And in order to combine the two together, and the materials include the internal process as DTXI, which is previously in the thermodynamics. So now I can see that if we wanted to integrate, so the quantum mechanics kind of standing alone, right? So now if we can put it all together, then we can have a coherent framework to predict the thermodynamic properties of energies of a system. Okay. So now we're going to combine the cathode modeling is mostly based on experiment before and estimation with modeling. And then we could integrate the quantum mechanics from first principle calculations based on density functional theory, because first principle calculations are usually for 0 Kelvin. So we have to add statistical mechanics to do the finite temperature calculation. In this way, we can enhance the predictability of the thermodynamic databases. So let's look at the DFT calculations. DFT calculations for the ground state configuration, which means that for any system, the stable state has the lowest energy at the 0 Kelvin with a unique electrodensity electrodensity functions. So what happens at T equals 0 Kelvin? There's a unique electrodensity that gives a total energy of the system, has the lowest total energy of the system. When temperature is less than 0 Kelvin, then there is entropy. There are two entropy contributions for this ground state configuration, with electron contribution and a phonons contribution, with two different statistics. This way, we can calculate the total entropy of that configuration. And when we get the entropy, we can calculate the free energy. There's home energy equal to E, the total energy plus electron contribution plus phonon contribution. Then Gibbs energy is the F plus pressure times volume. So what are the challenges? What are the challenges? Challenges that the calculation for the predictions, the results for the predictions are not in quantitative agreement with experiments. So why? So it turns out, as I mentioned, Gibbs developed statistical mechanics. Gibbs postulated that the system is going to embrace every conceivable combination of configuration. That means there are a lot of different configurations. They are different from the ground state configuration. So what that means, this discrepancy between the prediction and the experiments could be that the ground state configuration alone is not enough. We have to find all possible configurations. That means we have to go beyond ground state configuration. So what are the symmetry breaking non-ground state configurations? So it's basically internal degrees of freedom, as we showed before. That's the d cosine. So it could be spin, polarization, atomic, short, long range ordering, defects like vacancy, dislocations, stacking faults. So if we follow Gibbs statistical mechanics, we find the entropy of the system is equal to minus the Boltzmann constant with summation of all the possible configurations with the probability, log probability of all the configurations. So probability of a configuration is equal to partition function of that configuration divided by Z. And from Gibbs statistical mechanics is EK minus F divided by KBT. And the partition function of the system is equal to the partition function of the independent configurations, summation of the independent configurations, and then we'll connect the total Helmholtz energy to the energy of each configuration. So what it means is that if we have a system, entropy of the system has different configurations. So the entropy of the system would be the KB, Boltzmann constant, summation of all the probability of all configurations and log probability of that configuration. So I call it top-down view. Then you look at the system, you see what kind of configurations the system embraces. So we have to realize those configurations are symmetry breaking configurations. That means each of them have different symmetry. However, as we said before, these configurations, their entropy is not zero. What does that mean? That means each configuration has its own entropy. Now, if we want to calculate total entropy of the system, we will have to add this entropy of each configuration, which is weighted sum with probability times that the configuration of that configuration, entropy of that configuration. Okay, so now you see different, right? So this is from the Gibbs statistical mechanics, and now we have to add additional entropy, which are from each configurations, all configurations. Okay, so we can calculate those configurations, those configurations from density functional theory, as I showed before. So now we see we have two views. We have the top-down view is to see how many configurations the system has. Or from the bottom-up view, what is the entropy of each configuration? We put them together, now we can calculate the total entropy of the system. So we call this one Zentropy. It's basically cost greening of the entropy. So you have different entropies, entropys of different configurations. You cost green together, get the total entropy of the system. Now it has two contributions. One is the entropy of each configuration, and that is the configuration entropy among the configurations. So let's look at this, the Gibbs statistical mechanics. We have entropy is the summation of probability of each configuration. Then we get the Helmholtz energy, which is the EK, the total energy of each configuration, plus entropy. And then a partition function, then a probability of each configuration. Now, what's for the Zentropy side, now because each configuration has non-zero entropy, so I have to add that entropy into the system. When we add that one in, then the Helmholtz energy of the system becomes this, which is sum of the Helmholtz energy of each configuration. So you can see that instead of E here, we have F. And then you can calculate the partition function again, we have to use F instead of E. And the probability will also be calculated use F instead of E. So this two seems different, right? But but why? Or are they actually similar? They are actually identical if SK equals 0. When SK equals 0, that means each configuration has no entropy. That means each configuration is pure quantum state. Okay? Ultimately, are pure quantum configurations. That means without any unspecified degrees of freedom. That means it's only one configuration. Each configuration has no entropy, zero entropy. They call it pure quantum state. Because no more degree of freedom in that configuration. So let's see how we can apply this entropy theory for rares and the compounds. Okay, so for rare segments and the compounds, the quantum state configurations is either ferromagnetic, antiferromagnetic, or non-magnetic. Okay. Then the symmetry breaking non-ground state configurations would be spin flippings, right? So it's not purely ferro, not purely antiferro. So that means the spins are disordered. So for each configuration, we can calculate the Helmholtz energy. We can predict from the DFT. Okay. Then we can use that Helmholtz energy in the partition function of the configuration. So if we want to do that, we put them back together, use the statistical mechanics. I will demonstrate that we can have a quantitative prediction of the free energy without models on the fitting parameters. So in that case, we produce the Helmholtz energy of a phase with partition function of configurations. With Helmholtz energy of, then we also get a Helmholtz energy barrier between different states of the system. Okay, so with the canonical ensembles of all configurations. Then when we get the Helmholtz energy of the system, we can do derivatives of them, get all the properties. And we can calculate by minimization of by minimizing the Helmholtz energy, we can get a phase equilibrium too. So let's look at the Cerium phase diagram. There's a temperature and the pressure phase diagram. So we can see I have three phases, gamma, alpha, and beta. So let's temporarily forget ignore the beta phase. Okay. The ground state configuration of cerium, basically 0 Kelvin, 0 pressure, is non-magnetic. That's actually the own element. It is non-magnetic. Then at high temperature becomes a magnetic, which is ferromagnetic in this case, gamma phase. And also it has critical point. Okay. So it has not been predicted in the literature so far. So we know that between the ferromagnetic and non-magnetic, so we may have another intermediate configuration, it's antiferromagnetic. We published 2 papers on this system, which it's 2008 and 2009. So what happens that we have 3 configurations. The red one is the ground state configuration, has the lowest energy, has smallest volume. Then this is ferromagnetic at high temperature, high volume, high energy. So it's not the ground state. It has different symmetry, right? The spin symmetry are different. Then between we have the AFM, antiferromagnetic. You can see that the energy is the lowest one, second lowest one, the highest one. So we calculate the range of them, okay, of the different of the all configurations. Then we do a partition function. This is entropy, a partition function. We can calculate the entropy, the free energy at different temperature. Okay. So you see this light blue area is that's the configuration entropy. That's the statistical entropy among the configurations. Now you see that we have the common tangent to the equilibrium at 0 Kelvin, and then when temperature goes up, you can see that it gives energy. Now you have this double well, right? It's a minimum here and the minimum there, and then you can see that, however, when temperature goes up, there's a maximum gradually disappears. Basically disappears. When it disappears, we get the critical point, because now we only have one minimum on the free energy curve. So now we can, through this common tangent, we can construct a phase diagram. Okay, because the slope here gives the pressure. So it's negative pressure. Okay. And then it goes to 0 pressure, then positive pressure. Okay, positive pressure. Okay, so now you see that if you shove this line to the 0 Kelvin, you get negative pressure, and then you get 0 pressure. Okay, then you can see transition goes up here, and then at the high temperature and high pressure, we get a critical point. Okay, the symbols are here from experiment, the lines from the prediction. Again, there's no experimental input in this prediction. There's no models even. Just have the free energy function, use partition function, free energies of the 3 configurations, and the partition function of them, partition functions of them, and the partition function of the system. Then the energy minimization. Now we can see that we can change the pressure to its conjugate variable, its volume. We get another diagram, temperature volume phase diagram. Now we see that the critical point becomes a maximum point here. When temperature below this critical point, we have the 2 phase equilibrium. Okay, so one of them has smaller volume and another larger volume. So this side has to make this side is more ferromagnetic, and this is less ferromagnetic. But all of them are the mixture of the 3 configurations. It's not a single one. Until you go to 0 Kelvin. So we can also get the equation of state of the cerium. As you can see that this is the different temperature, and this is the property of volume as function pressure. Okay, symbols of experiments again. And you see, if this red line here is the minimization of energy. If one does not do the minimization of energy, you get this nice curve. Okay, so you can see that you can have equilibrium. You can separate phases. You separate the 2 phases here. For example, look at the dotted line, a dashed line. You see they separate. You have phase separation here because energy will be lower by that process, the minimization of the homogeneous energy. So it's very nice agreement with experiments. Remarkable. Again, is no model, no fitting parameters. And it's really this entropy, right? We have 2 entropy contributions here. Okay, so you can see here. So we have this is the total entropy compared with the experiment data. So this is for only the phonon and the electron contribution. Okay, and the lattice contribution. They're different. So we really have to add this one together, okay, to get this total entropy. That's very important. So that's why the DFT only get this one, okay? So it's not enough. You can see the electron is very small, but mainly lattice phonon contribution. So that's why the DFT alone for the ground state, okay, is not enough to reproduce to represent the total entropy of the system, okay? So this is the energy difference. Again, you see the T delta S is very important. Okay, so it's going to be huge impact on the energy. Again, the symbols are from experiments, and it's aligned from our calculation. So you have 3 contributions. Total energy. You have total energy contribution. Okay, that's the red one. Then you get the P delta V contribution. Then you have the T delta S contribution. You can see that the T delta is extremely important to get the energy correct. Now, and that we also apply to another alloy, which is not rare earth, but I want to emphasize here for the INVA alloy has negative sum expansion. This is experiment. The symbols are experiments. The linear sum expansion at 0 Kelvin is 0. So when temperature goes up, temperature increasing, and it's increased to some expansion, and then decrease, then become negative. Okay, then the minimum then become less negative and become 0 and going forward. So you can see that these lines again is completely predicted. So for iron 3 platinum, again, we have the spin configurations. So this is ferromagnetic, is the ground state. And then the other spin change configurations are the non-ground state configuration, a symmetry breaking, I can see for the spin polarization. So I have 9 iron atoms, so 2 to the 9 power, by 512 spin configurations. But because the symmetry of 37 are unique, so we can calculate this the 37 energy, like this at 0 Kelvin, the total energy as function volume. You can see that this time the ground state has a larger volume than the non-ground states. So it's different, it's opposite of the serial. Okay. So kind of free energy shows that the ground state is stable, has low state of free energy at all temperatures. At all temperatures, free energy different divided by kBT. So if you just use energy, there should be no transition, right? So the ground state will be stable all the time. However, we know that we have transition. Again, that's because this is non-ground state configurations, we have the probability will increase. Okay, as we show here, there's a probability of the different configurations. At 0 Kelvin, 100% ferromagnetic state. Okay. However, temperature increases, you can see the percentage is going to decrease. Probability, okay, decrease, even though it's still low state energy. So all the other configurations combined together is this dotted dashed line. So 2 of them are shown here. It's highest probability. There are many other ones. Put them together, 512. So value them together at this temperature, it will become, even though the ferromagnetic ground state is stable, energy is lost, but the probability will decrease below 50%. Okay, we can also have the Barker modulus at different pressure. And again, this is remarkable agreement with experiments. So for different pressures. And now we can calculate temperature pressure phase diagram. Just we can get a free energy calculation. So we find that this pressure is the product in the increased pressure here. So you can see that we get a second order transition, and again the simple side experiment and the first order transition. It's amazing that the agreement is remarkable. Again, considers no feeding parameters, even no model. It purely is the range of different configurations of density functional theory, DFT, and then put them together by statistical mechanics. Now, if we change the pressure to volume, okay, the larger volume, the larger pressure is smaller volume, right? Smaller volume, larger pressure. Now we see that the critical point is here, okay, and now you see that below the critical was the first order transition going to be split gap, and then there's a second order transition. Now the interesting is that at the given different pressures, three different pressures, four different pressures, and at 0 pressure, ambient pressure, when temperature increases, volume increase first, and then start to decrease, they increase again. So in this purple area, we have negative thermal expansion. So that will reproduce exactly what we have here. So that's a line here at the ambient pressure. Now, of course, I forgot to mention that in Syrian case too, that at this critical point, so the expansion becomes infinite. In this case, a negative infinite. In Syrian, it's a positive infinite. Okay. So divergence. Again, that's predicted from Zentropy theory without any feeding parameters. So the next case is it's rare earth nickelate. The people use in the community, we believe in the community, we believe that is strong correlated physics. It's a complex. So this is temperature with different tolerance factor, basically different electron contribution. You can see that for different rare earth elements, okay, we have 2 transitions. One is the magnetic transition with the same crystal structure. Okay, changing for insulator, the insulator, but from the antiferromagnetic to paramagnetic. And if you extend it further, it is a paramagnetic from insulator to metal, the conductor, but it changes crystal structure. Okay. And if you go above this one, then this transition does no longer exist, directly from the antiferromagnetic insulator to paramagnetic metal, and with different crystal structures. So what happens is that you have this kind of octahedral. Okay, so you have nickel in the middle, you have oxygen, then you have the green ones are the rare earth element. So if you look at different direction, look like this. You have this kind of a distortion. You see, you have smaller ones and big ones. Okay. So there's nickel ones, some of the octahedral are small, some of them are large. Okay. So we'll look at each uniconate. Okay, each uniconate. This is for each uniconate. And there's small ones, smaller nickel octahedral is the nickel has no spin. Okay, it's zero spin. It's not magnetic. It does not have magnetic spin. Okay, so you see this one have no spins. The ground state, and then you have this spin up nickel and spin down nickel. Okay, so it's ground state. It's antiferromagnetic. It's number 45 out of our structures. So we have 258 spin configurations, and 37 unique. This is the paper published last year. So one of them, the second lowest one is another AFM, which is 20.2 MeV energy higher than this one. Now you see that the polarization becomes a little different now, right? So it is this three, okay, and that's three. So you see, if you look at this direction, so basically look at this one, right? So this one spin here. It changed now. It changed spin, change opposite direction, and opposite direction. Okay. So this change. Okay. So this has 20.2 MeV. So it's pretty low energy. We can calculate the energy. Another one is the FM state, ferromagnetic state, is much higher, it has 21.6 MeV, higher than the ground state. So now we have this 37 of them. We can calculate all the total energy. Okay, so number 45 has lowest energy. FM is up here. Of course, I have some other high energy ones. And then we calculate the energy. We, for example, plot at 150 Kelvin. We can plot the energy. The 45, the ground state is still the lowest energy. Then we do the ambient pressure, or the Gibbs energy as function, as a Gibbs difference as a function of temperature. We see the ground state is always stable. Okay, but the difference between the different configurations becomes much smaller because it develops a KBT. Then we calculate the probability. Again, the ground state is 100% at 0 Kelvin. Then when temperature increases, the probability decreases and reaches around 50%. Okay, so which is 50% is one of the criteria we use to judge the phase transition, because it means that at this temperature, the ground state is no longer majority, or it's still no longer majority. It's less than 50%. So it loses, it lost the percolation. However, if we use the Gibbs statistical mechanics, use the total energy, we find that the crossing is much lower temperature at 81 Kelvin. So if now we can plot the temperature pressure phase diagram, and if in this case, all the transitions are second order. There's no first order transition. As you can see, the lines don't cross each other. Okay. So it's all second order. So the predicted temperature is 45. The experiments predict 144. the experiment 145. It's very close. Again, as I mentioned, if we use the total energy, it's 81 here, 81 Kelvin. It's way off from the experiment. That's why people could not predict the transition use the density function theory alone. We have to put the statistics and the DFT together. We have to consider all possible configurations. And we can also calculate short range ordering. Yeah. The sampling, we can short range ordering too. And it turned out, again, you look at it around the transition temperature, you go to 50%. It's pretty close to transition temperature. When the short range ordering becomes 50%. Okay, so we have been developing this kind of tools and methods to generate data. Okay. So we have as I mentioned, we have density function theory. We also have developed machine learning models, okay, and connected with the data consortium as Optimate. And we're not developing the Zentropy. Hopefully we can finish them next year. And we also have the data repository for experiment data. And when we get data, we have the processor. Okay. Now we have PyCap to develop the Kappa databases. We can also do uncertainty quantification. When we get all this data together, we can do inverse design of materials. We have a demo here showing this website, HTTPs and CGAN demo.atra.org. We'll also organize workshops to teach the community how to use the tools we develop. Okay, so what's the next step? We've got the energy, right? So we get not only free energy, we also get the energy landscape. Okay, that means we also get the energy barrier. Okay, so then we do some we know something called some phenomena, direct phenomenon is between the conjugate variables like temperature, entropy, pressure, volume. But often we also get this cross phenomenon between non-conjugated variables. So let's take temperature as an example. Direct one is heat, entropy, conduction. Then if we have the electric current, atomic diffusion, volume flow by temperature gradient. For electric field, we have the electric current and direct phenomenon. We also have the cross phenomenon, electric conduction for heat conduction, atomic diffusion, and strain change. That's the electromechanical properties. For stress and pressure field, we could have the volume and the fluid flow, stream flow. Then we have those cross phenomena with electric current. You press it to get electric. That's the piezoelectric. And the atomic diffusion and also the heat conduction. Okay. Oh, this is repeated, same slide. And it's now we developed the theory of cross phenomena. Is that if you know the Onsage theorem, is that flux is the flux of one molar quantity is proportional to all gradient potentials. However, we have realized that the molar quantity flow is only driven by its conjugated potential. But also we know the cross phenomenon. So what does cross phenomenon come from? Well, it's because this gradient potential, the gradient of the potential is a function of other quantities. For example, we talk about diffusion. The chemical potential is a function of its composition, but also other compositions of the other element, or the temperature gradient, or the electric field. Okay. But the difference between this one and that one is that here we have molar quantities and some potentials, but here's all potentials, so that's incorrect. For if it's only potential, it's only one potential. Okay, you can see that flux now is a function of many variables. That's also cross phenomenon, but at least one of them must be molar quantity. Okay, so I want to conclude my talk is that now we have a quantitative predictive theories, a Zentropy theory. We can predict free energy landscape using the quantum mechanics and statistics thermodynamics without fitting parameters. So because now we get this barriers too, okay? So we can calculate the barrier between different states of the system. And then when we got the free energy, we can do derivatives to calculate properties and also calculate this cross phenomenon, like the Seebeck coefficient and solid coefficient. We have a number of papers on that. So now we get these tools. What's next? Well, in this paper published this year, I discussed about, I reviewed the thermodynamics and discussed state of the art and those perspectives. Okay, basically that we can use the Zentropy theory to predict the free energy without experimental inputs. That means we can now start to design new material and then discover a new material. So that was material design, which is another paper written by Professor Olson and me, as published in the same year, same journal. So if we put them together, it's really the system-based, data-driven to computational material design. Thank you.